In this video, I'll be showing you how to set up a simulation with a coating or a film. Let's start with a basic static structural analysis. Oftentimes, companies ask me about how to model films or thin coatings because for thin sheets of geometry, sometimes having thin coating can greatly can introduce a residual stress, which causes deformation on thin features like glass plates or very thin films. So this is discovery modeling. We're going to create a thin piece of geometry. Let's make it 80 by 30. And we'll create a fairly high aspect ratio part of just 1 millimeter in thickness. And if we want to add a film, I do Control C, Control V to create a surface on top of the solid. We can put this into a single component. And we can turn on share topology. So share topology will ensure that the surface and the solid is meshed with a conformal mesh, and that means we can treat the shell or the surface as a coating. Okay, here's our model. We want to go ahead and set the properties of all of these parts. So I'm going to look for some plastics for my solid, which if I go down here, you can see there's various types of ABS, HDP, PE, and polyamides. So let's go ahead with a ABS plastic here, and let's say we're going to do a 10 micron layer of copper. Here we go. Go for a basic copper alloy here. So you can see there are no connections between the parts because they are going to be connected node by node. Slightly darker gray for the copper, slightly darker gray for the plastic, and this bluish gray for the copper. We can also display the node numbers. You can see that each node in the corner has just a single number, so these are sharing the nodes between the parts. Turn that off. Now we want probably three layers of thickness of elements in the copper, so I'm going to put in a method here. Go for a sweep method, and we'll do 3 layers through the thickness. Okay. Now we have a model here. I'm going to turn on weak spring, which will tend to hold the part in place. Select the blue section, and I'm going to put a temperature on there. This will allow me to specify a pre-stress of the part. So if initially, let's say this is 100 degrees, then we cool it down, let's say a delta temperature change of minus 100 degrees. This will tend to contract, that'll pull the rest of the part upwards. So we should have a smiling shape here. The benefit of this method is we can make the surfaces as thin as we like. Right now it's just a tenth of a micron, but you can, 10 microns, but you can make it a nanometer if you'd like here. Let's look at the total deformation. Right, so it's behaving the way we'd expect, with the top surface contracting, pulling it downwards. We can also look at the stresses on the film if we wish, and the strain. Let's grab these results. Okay, so that's the top and bottom stress distribution and elastic strain. So very similar. Because we can assign material properties to the surface, you can see there's stiffness options for membrane only, membrane bending, or stress evaluation only for that shell. We can also make it nonlinear if we wish. So that's a simple model here. Let's say we get rid of this part and we make, let's say, a curved surface. So let's say we do something like this. I think I want to cut this a couple times and trim. Create corner. Do trim away here, so get rid of these things. And I'm going to do an offset here. So rather than having a straight piece, I'm going to show you how we can do the same model but with a curved piece section. Okay, so if we hit the P button to pull, we're going to revolve this around this one, and we're going to just have it go around the whole circle. So now rather than a flat piece, we have a dome. So let's see what happens when we have a dome, and I'm going to copy paste it. We have a surface here on top of our dome, and this time I'm going to make the whole analysis, whole assembly with shared topology. So I'm going to update my model. Okay, so it's just telling me, hey, there's all these things that needs to be changed. So let's go ahead and fix the changes. So that's the sweep body. Okay. Say 100 microns. We're gonna do copper and ABS again. Let's go ahead and generate the mesh. So maybe we do, instead of sweep automatic, we'll do a thin, automatic thin. See if this does a better job of meshing it. Okay, so it's got the surface as well as a solid mesh on the inside. We're going to select our orange color surface here and solve the simulation. So you can see the way that this, let's get rid of our edges here. You can see that the way this particular film surface causes the plastic to deform. We can look at the stress. This is stress on all the body, so I can reduce that to just the stress on the surface itself, as well as the stress on the solid. Okay, so that's the stress on the surface and the solid. We can export this deformed shape as an STL file for further processing if needed. So that's a quick example of how we set up a film stress simulation, pretending that if you either painted or coated a solid with a very thin layer of another material, how do we model the deformation when that thin layer has a significant amount of residual stress. Hopefully you found this video interesting. If you